Okay, so let me get started with attendance. Please answer your attendance. Aditya Kumar,
Present, sir.
Anand,
Yes, sir.
Ananta Kumar,
Present, sir.
Arnachalam,
Yes, sir.
Hasan,
Present, sir.
Hemant,
Present, sir.
Jagan,
Yes, sir.
Kesav Prasad, Lakshmi Narayanan,
Present, sir.
Prabhakaran,
Present, sir.
Prem Vinayak,
Present, sir.
Ragul,
Present, sir.
Roshan Kumar,
Present, sir.
Sabish Kumar,
Present, sir.
Satish Kumar,
Present, sir.
Titus,
Present, sir.
Valish, Vigneshwaran,
Present, sir.
Vijayaraj,
Present, sir.
Vikas,
Present, sir.
Vivekanand,
Present, sir.
Yadav,
Present, sir.
Yuvraj,
Present, sir.
Fine. There are two absentees today, Valish, Kesav Prasad. Okay, so welcome back to this class. We are in chapter 3. We are now discussing about SI engine combustion. In this chapter 3, so far we discussed about overview of combustion process in spark ignited engine. Then we discussed about the different stages of combustion. We understood that the combustion event takes place in 3 distinct stages in spark ignited engine. That has to be concerned with the formation of flame, stable flame, propagation of flame, and termination of flame. After understanding these different stages of combustion, we analyze various factors, engine design based and operating condition based factors that affect the different stages of combustion. Our focus was on stage 1 and 2. The second stage, almost 80% of the charge is burned. The first stage is concerned with forming a stable flame. So it's very important to know the factors, engine design and operating variables that affect flame development as well as flame propagation. So in the previous class, we discussed about these factors. We understood the various factors that help us to control this flame development and flame propagation. As we discussed earlier, we don't want instantaneous combustion in SI engine. What we need is a progressive combustion. And now we understood the various factors that help us to control these different stages, okay, in a progressive SI engine combustion. So with this, we would be able to better control the combustion event. The idea behind controlling the combustion event is there are 2 objectives. So one is about improving the engine performance, and second one is reducing the pollutant emission. So we need to better control the combustion event so that these 2 objectives can be achieved. Okay, so today I'm going to start an important discussion about cycle by cycle variation in SI engine combustion. SI engine, spark ignited engine, unlike diesel engines, they are subjected to large cycle by cycle variation. Okay, cycle by cycle variation in the combustion event is one of the undesirable phenomena that happens in spark ignited engine. In diesel engine, in compression ignition engine, the cycle by cycle variation is minimal or negligible. However, it is a significant problem in SI engine combustion. Okay, so what I mean by cycle combustion variation is, if you could look at this pressure crank angle diagram, I have given 2 diagram. One on the left side is an ideal pressure crank angle diagram, ideal from the perspective of no cycle by cycle variation. You could see that there is only one profile. This profile, pressure profile, is drawn for n number of cycle. This is drawn for n number of cycles. So you know, so what I mean by cycle here is one engine operating cycle. Okay, so one engine operating cycle. In a 4-stroke engine, one engine operating cycle include 4 strokes, right? And what are the processes involved?
Suction, compression,
Power and expansion.
power stroke, and then exhaust.
Yeah, so there is an intake, compression, followed by expansion, then exhaust. Everything put together is one operating cycle for a 4-stroke engine. So engine execute n number of operating cycle. What will decide the number of cycles in a given time? So when you talk about number of cycles in a given time t,
RPM,
what will decide that?
RPM, sir.
Engine RPM. So engine running speed will decide the number of cycles executed in a given time. When the engine runs at high RPM, you are going to execute more number of cycles per unit time. Okay, per unit time. So what I have given here on the left hand side is only one profile which is drawn for n number of cycles. So this diagram is drawn for n number of cycles. N number of engine operating cycles. Say for 100 cycle, I am getting only one profile, meaning all the profiles, pressure profiles for n number of cycle collapse as a single profile. Collapse as a single profile. So I have only one profile for n number of cycles. Say 100 number of cycles, I have only one profile. This is an ideal case. This is not an ideal in the perspective of constant volume combustion. Here by ideal I mean there is no cycle by cycle variation. This is what I mean by ideal. So there is no variation in the pressure profile from one cycle to other cycle. You have only one smoother pressure profile. Okay, so this is an ideal case. But how it will look like in an actual spark ignited engine is shown on the right hand side. So here you have, this is case 1, ideal. Case 2 is actual. So this is how the pressure profiles look like when you draw it for n number of cycles. Okay, suppose if you draw the pressure profile for say 100 cycle, you will see that from one cycle to other cycle, the pressure profiles are not going to overlap as you are seeing in the ideal case on the left hand side. In actual case, you will see that there is a considerable difference in the profile, pressure profile, as you could see here. So this is say for cycle 1, this is for cycle 2, this is for cycle 3, and so on. So these are drawn for n number of cycles. Okay, so you could see that there is a considerable difference in the profile for one cycle compared to the other cycle. Okay, as indicated here. And this is what I mean by cycle combustion variation. From one cycle to other cycle, there is a considerable difference in the pressure profile. This is what I mean by cycle variation. And this is one of the undesirable phenomena. What effect it will have, I will discuss later. But now, can you think of the reason for such a variation in the pressure profile from one cycle to other cycle? Now, since we have understood the combustion phenomena in SI engine, based on your understanding, can you highlight what could be the possible cause for this cycle variation?
The fuel air mix composition, and then some hot spots in the within the engine walls, pistons, etc.
So
So
hot
if you look,
spots in the engine and fuel compound different. Okay.
So
load under which engine is getting operated, like it's whether it is a very what I meant to say is low load condition or high load condition.
No. This is not. This profile is drawn at a particular load, particular speed. Engine operating condition is fixed.
Sir,
Okay. So this is at a particular load, particular operating speed. Even then, there is a variation in the profile.
sir, mechanical losses may be slight difference in valve timing, valve closing timing and opening timing, and leakage in different cycles. The difference in some leakage, piston leakage. So that may be the reasons.
Okay, so you are talking about system level changes from one cycle to other cycle, but generally system level, the engine system is so precise, especially if you have an electronic control system. I am asking you to think from a process perspective. Having understood the combustion process, from the process perspective, is there anything happening? I said I have given a hint. This problem is severe only in SI engine, not in CI engine.
Mixing of homogeneity of charge, sir, basically.
Homogeneity of charge, okay.
And then what I mean to say is, if the spark energy is varying from cycle to cycle, suppose because of some other conditions like.
Now that's why I say that system level changes are minimal, because you have a very precise system, control system in engine. Current level of control is so precise.
Okay.
It has to do only with process, not with system. Okay. Something related to the combustion process in SI engine, which we have already discussed.
Then homogeneity of charge is coming to first in your mind.
Homogeneity, yes. Homogeneity will play a role. Anything else?
Intensity of discharge, sir.
Intensity of spark discharge, again, that is precise. So what I mean to say here is, at a particular engine operating condition, say load and speed are fixed. But if I draw the profile from one cycle to other cycle, I see a considerable difference even at the same operating condition. This is what I mean by cycle variation. So something has to do with the combustion process in SI engine that is causing this large cyclic variations. See, the combustion process, if you recollect what we have discussed, combustion process in a spark ignited engine is based on how we are forming a stable flame around the spark plug region. The flame formed in the spark plug region is going to propagate across the combustion chamber. Okay, so there is something called flame development period, which we have discussed, that is stage 1. And there is something called flame propagation period, that is stage 2, right? This is what we have discussed, right? And finally, flame termination. So the overall combustion event in a spark ignition engine is based on how we are forming a stable flame, that is stage 1, and how the flame moves across the combustion chamber, that is stage 2. What is happening in a spark ignited engine is, it's very difficult to maintain identical charge composition near the spark plug location where you are discharging electric spark. From one cycle to other cycle, there will be variation in the mixture composition. So this is mixture composition, GLR mixture composition. In the spark plug location, this is where you are discharging electric spark, right? When I say fuel air mixture composition, what I am saying is there will be variability in fuel proportion, there will be variability in air quantity, there will be variability in the residual gas fraction. We already discussed about residual gas fraction in the previous classes. Okay, residual gas fraction is the exhaust product that remains in the engine at the end of one cycle. Ideally, we want all the exhaust to leave the engine at the end of one operating cycle, but there will be some quantity of combustion product that remain in the cylinder. That's why it is called residual, remain in the cycle. I said it is around 4 to 8% generally. This is a nominal range of this residual gas fraction. So the proportion, mixture proportion in the spark plug location where you are discharging electric spark is going to be different from one cycle to other cycle. Why? Because there will be slight change in the fuel proportion that goes here, slight change in air proportion that goes here from one cycle to other cycle, and there will be change in the mixing process from one cycle to other cycle that will result in variation in the P value in the spark plug location. Okay, so it's very difficult to create homogeneous mixing from one cycle to other cycle. Okay, and there will be variation in the residual gas fraction in the spark plug location from one cycle to other cycle. So there is a change in phi from one cycle to other cycle. Any change in phi will directly affect the flame development period. So there will be slight variation in the flame development period from one cycle to other cycle. Also, I already told you that you are locating spark plug within a recess in the combustion chamber. So there will be something called a recess. This is the location where I'm sorry. So I'll just rewrite. So what you do is, so this will be, there will be a slight recess in the cylinder head, and this is the location which has this spark plug. Okay, because we want to isolate this region from rest of the region. Rest of the combustion chamber will have appreciable fluid motion. Appreciable fluid motion during the flame development time will affect the flame stability. So we don't want any appreciable turbulence in the spark plug location. This is one of the variables we discussed in the beginning when we discussed about the factors that affect flame development. we said we don't want turbulence at the time of flame development. Any turbulence here will affect the stability of the flame during the development time, right? So near the spark plug, although we locate it in a recess and we want to isolate this region from rest of the region, there will be some fluid motion near the spark plug region, and this affect the heat loss from this location. Okay. From one cycle to other cycle, there will be slight variation in the fluid motion near the spark plug location. So there are two variabilities here. One is the mixture composition defined by phi in the spark plug location. This will vary slightly from one cycle to other cycle. And the second variability is the fluid motion near the spark plug is not going to be identical in each cycle. There will be slight variation in that, and that in turn will affect the heat loss. Okay, so the overall effect is there will be change in the flame development period from one cycle to other cycle. And you know, flame propagation follows flame development period. It's a subsequent process. Any change in flame development time will affect the flame propagation time because this follows flame development period. Did you get what I am saying? These two are subsequent process. Any change in stage 1 will affect stage 2 time. Is it clear?
Yes,
Yes, sir.
Yes,
So,
yes, sir.
so there will be variation from one cycle to other cycle in the flame development period, and there will be variation in the subsequent flame propagation from one cycle to other cycle. This is what you are seeing here. This effect is what you are seeing here in terms of variation in the pressure profile from one cycle to other cycle, because you cannot maintain identical flame development time or period and flame propagation time or period in SI engine. Since it's a flame propagation based, flame development and flame propagation based combustion phenomena, you cannot maintain it identical for each cycle. That's why you have variation in the pressure profile from one cycle to other cycle. This is what I mean by cycle combustion variation. Okay, so this is what is a problem, and this problem is predominant in spark ignited engine. Okay, as compared to CA engine. In CA engine, it's not a flame propagation based combustion even. We are going to discuss in the next topic. It is not flame propagation based. That's why you don't have this problem. Okay, so the differences in the charge quantity, fuel air mixing, the differences in the residual gas fraction affects the composition of the charge in the spark plug electrode gap. This is the primary reason. Second reason is the fluid motion near the spark plug also affect heat loss, and thereby the flame development time varies from one cycle to other cycle. Okay, so this is the cause for this problem. Cause for this problem is provided here, and what effect it will have on the engine? Can you tell me? What will be the effect of this cycle by cycle variation?
Emission, sir. Emission will be different
Pollutant emission will be different. Okay.
from cycle to cycle.
In terms of performance, are there any effect?
Yeah, there will be a power loss, like because the spark produced plays like the flame. If the flame propagation takes time, then the maximum pressure built up in the combustion chamber will get affected, and then finally it will also affect the output torque.
Exactly. So this is one of the most important effect. There will be power loss. Large cycle by cycle variation leads to power loss in SI engine. Okay, this is one of the detrimental effect on the SI engine due to cycle by cycle variation. Okay, so you will have a power loss, as you could look at, as you can see from the profile, pressure profile. Okay, so you could see that some of the cycles. So you see the slope. This cycle is a fast burn cycle. You see that the slope is very steep. Okay, this cycle burns quickly. It's a fast burn cycle. You see this cycle slope. It's a slow burn, right? Slope is flat. It's a slow burn cycle. So you have a large variation in the profile. Some of them are fast burn cycle, some of them are slow burn cycle. We discuss about MBT timing. You are optimizing spark timing based on the engine running condition. At a given speed and given load, you have one optimal timing. You are not optimizing this timing based on cycle by cycle variation. Please remember, you are not optimizing this based on cyclic variation in combustion. Rather, you optimize this based on an engine running condition. At a given load, given speed, there is only one MBT timing. Okay, because of this fast burn and slow burn cycles lead to power loss. Fast burn cycle, how the fast burn cycle lead to power loss?
because the Pmax will be near to TDC and the compression work done by piston will be higher.
Exactly. Compression work will be high. So this increases negative work. Compression work, I already told you that it is a negative work because it's work done by the piston. Fast burn cycle will increase negative work because there is more work done during the compression event. Since the rate of burning is high, the combustion started early and the piston has to do more work against the expanding gases. What will be the problem with slow burn cycle?
Again, the power loss, sir, because the
Yes, sir.
Peak pressure will be lower.
peak pressure will be very
Pressure is lower. So P max is considerably less here. So this will have loss of expansion work. Slow burn cycle will have loss of expansion work because P max is less. Fast burn cycle will have loss of work or power due to higher negative work. Piston is doing more work, okay, to compress the expanding gases. Combustion started early, piston is moving up, the gases expand and try to push the piston in the downward direction. So piston is doing more work with fast burn cycle, and the work done by the piston during expansion stroke is reduced with slow burn cycle. So there is a loss of expansion work. Overall effect is power loss due to large cyclic by cycle variations. And since you are not optimizing the timing, spark timing based on individual cycle, rather you do it for a given engine operating condition, you end up in getting power loss in SI engine. This is the overall effect of this cycle by cycle combustion variation. Since it's a flame propagation based combustion event, this is one of the problem with these kind of combustion. There will be large cyclic variations leading to power loss. And this effect is more dominant at low load. Effect is more dominant at low load condition. Also when the compression ratio is less. At low load and low compression ratio, the cyclic variation will be very high because at low load, we already discussed that there will be dilution of the fresh charge due to reverse flow of exhaust gas. If you recollect what we discussed about the phenomena happening during valve overlap period at low load or park load condition, there will be reverse flow of exhaust gas into the intake system. So this is going to dilute the fresh charge. Any dilution of the fresh charge will increase the residual gas fraction. Okay, and thereby higher residual gas fraction leads to composition variation in the spark plug location. Okay, so at low load, the variability is high because the dilution is very high at this condition. Compression ratio also affect residual gas fraction. We already discussed about that. Higher compression will lead to higher expansion, less residual. But lower compression, the opposite effect will be there. You will have more residual, thereby you will have a large cyclic by cycle combustion variation. Okay, so this effect is more prominent at low load and low compression ratio. Now, what is the solution for this? How do we address this? This cannot be avoided. You cannot completely eliminate cyclic variation. This is unavoidable. But what we can do is we can minimize this. We can minimize this and try to approach the ideal case. Right? What should we do to minimize this?
So increase the mixer. Like what I mean to say is inject little more fuel, make it richer a bit.
So create high temperature condition.
Right.
That's what you are saying.
Right, sir. Right, sir.
Sir, to have higher inertia.
Higher inertia. What is that? Higher inertia?
Inertia of the system, sir. Basically, mechanical system.
How does that help?
It will reduce the variations, sir, because of combustion.
I'm trying to understand why do you say that variation in inertia of the mechanical system reduce variability? This has to do with the process, right? How the system level inertia affect this process.
Right.
I think he's trying to correlate it with the speed at which the components will move and.
Okay, speed. Okay, speed will have definitely some effect. Fine. Anything else?
Sir, you are told
instead of single spark, like go to digital, like DTSI, all this, like twin spark and all.
So spark plug location and spark plug, the number of spark plug that you use will play a role. So these are the various countermeasures. So you can go with dual spark plug. You could have seen in some of the motorcycle, dual spark plugs are used, right? Bajaj extensively use this. So this dual spark plug will reduce the variability because the flame, sorry, you said something. Okay, you are using two spark plugs here. Okay, instead of one, you have two spark plug, meaning you are generating two flames at two different locations. This will reduce the combustion duration. This will enhance the flame, charge bond duration considerably because you have two flames in this case. Okay, so this will considerably reduce the cyclic variation because the bond rate is going to be enhanced. Increase the engine speed. Any increase in engine speed will enhance the mixing, fuel-air mixing, will enhance the flame propagation speed. And this is going to reduce the variability, cycle by cycle variability. Turbulence level also will play a role. Increase the turbulence level by suitably shaping the combustion chamber. Earlier we discussed how we can create turbulence during intake and compression stroke. Okay, by suitably designing the combustion chamber, you can increase turbulence level, increase the flame speed. Okay, this will reduce the variability, combustion variability. And also you need to have a better control unit. So you need to have better sensor with closed loop control. You have to monitor the pressure profile, how the pressure varies from one cycle to other cycle. So you need to have a closed loop control system with sensor that has to give feedback if there is a large cyclic by cyclic variability. So accordingly, you need to take countermeasures in terms of increasing engine speed, engine load. Also, compression ratio should be higher. Okay, these are the requirement that you can. So compression ratio, I will talk about it. You can have a fixed compression ratio as well as variable compression ratio. Variable in the sense you can vary the compression ratio dynamically when the engine is running. I will discuss about that later on. Okay, there are two parameters here. One is geometric compression ratio and the second one is effective compression ratio. Geometric compression ratio you cannot vary, but effective compression ratio can be varied based on the valve timing. Okay, so if you have a better sensor with closed loop control, you can monitor the cycle by cycle variation, and if there is a large variation, you can accordingly send the signal, appropriate signal, to take countermeasures so that you can minimize the power loss from the SI engine. Otherwise, there is going to be a large power loss because of this cyclic variation. It's unavoidable, but it can be minimized by properly monitoring with the help of effective engine control system.
Sir, I have doubt over here, sir. I'm sorry. Can I ask, sir, if you allow me?
Yes, go ahead.
Sir, basically, you had told that turbulence level in the engine is detrimental for flame development phase, whereas it is very advantageous for flame propagation.
Yes.
So here, sir, if we are having a cycle-to-cycle variation, and we have just discussed that if we increase the turbulence level, probably will help. But here you have told that it will depend on flame development as well as flame propagation both. So once the turbulence level is increased, sir, so flame development will have a detrimental effect on that.
Yes.
That particular parameter. So how it is going to help in that? How the net gain is?
You recollect whatever I said earlier about engine parameter optimization. You always have a trade-off. There will be positive effect. There will be negative effect. When I say increase or decrease, you need to, take it in the sense that it should be optimal, not too low. Okay, too high will lead to, in fact, power loss also due to heat loss. The very high turbulence level will considerably increase the heat loss, and there will be associated power loss. Okay, there is a different phenomenon from what we are discussing here. But in terms of the effect of turbulence, there are positive effect, there are negative effect. What is a positive effect? Positive effect is it will help you to create a uniform mixing, fuel-air mixing. Okay, and it will help you to enhance the flame speed, flame propagation speed. So the variability in the second stage will be considerably reduced. In fact, it is dependent on the variability in the flame development time. Because of higher turbulence, I said any change in turbulence will affect the heat loss. Okay, so you need to ensure that the heat loss is not too high because of the turbulence, right? Otherwise, the positive effect of turbulence is it will improve the mixing, fuel-air mixing in the cylinder. Okay, that is one effect. And second one, it will enhance the flame propagation speed. Higher flame speed will increase the burn rate, will increase the temperature in the cylinder. That will also reduce the variability from one cycle to other cycle. There are positive effects, there are negative effects. You need to optimize it.
And slightly richening the mixture will not help, sir, to reduce the cycle to cycle variation.
Slightly richening the mixture will increase the temperature, but that comes at the loss of, again, you only under certain conditions they will do richening of the mixture. For example, part load. I already told you about the dilution of the crush mixture. At part load, we do richen the mixture because at part load anyway the consumption of fuel is also less, right? If you slightly richen, it is not going to affect the overall power output. But at high load, if you richen, you will have a problem, because the quantity of fuel and air consumed is high at a high load, right? Under certain condition, you do that, okay? Especially at part load condition, because this helps in reducing variability, because it helps in reaching higher temperature.
Thank you, sir. Thank you so much.
Okay.
Sir?
Yeah.
Sir, I have one doubt, sir. Like, if we increase the amount of charge, amount of spark, generally it will go towards fast burning process, right, sir?
Yes. Amount of spark in the sense, what do you mean by amount of spark?
Like, no, that means spark, like, we are giving spark energy. So if we increase that energy, like for
talking about spark intensity.
Yeah, correct, sir. So okay. Spark intensity, then it will go towards fast burning process.
No, spark intensity has nothing to do with burn rate. Okay, spark is discharged only in nanosecond. I said I've given some typical numbers, right? At the time of spark discharge, few nanoseconds. Nanosecond, that is a time scale. Okay, so this is done only at that nanosecond time scale. I mean spark discharge. Whatever you do here is just to initiate the ignition. Okay, that has nothing to do with the development of flame or the time taken for forming a flame, stable flame. Okay, it is, you are just initiating it. That has nothing to do with burn rate.
Understood, sir. Understood, sir. Thank you, sir.
Okay. So we have discussed cyclic variation, which is one of the undesirable phenomena in SI engine combustion. Now we are moving to the next topic, which is about abnormal or knocking combustion. So again, this knocking combustion needs to be avoided because it leads, in the worst case scenario, it leads to engine damage. Now we are going to discuss about what is the mechanism behind this abnormal or knocking. Abnormal combustion is also referred to as knocking combustion. We will discuss about the mechanism involved that forms this knocking combustion so that we can avoid. Understanding the principle behind this knocking combustion is important from the perspective of avoiding this knocking combustion in SI engine. So we are going to discuss about the mechanism involved in this knocking combustion and what are the effects of knocking combustion and how we can avoid this knocking combustion. What are the factors that you can utilize to avoid knocking combustion is what we are going to discuss under this topic. So as said, this knocking is an undesirable phenomena. The basic principle behind abnormal or knocking combustion is self-ignition. What we want, how the ignition should happen in a SI engine in a normal combustion is, you discharge electric spark, initiate a flame formation. The flame should be stable. This flame should move across the combustion chamber and the flame should ignite the mixture. This is the normal smoother combustion that happens in SI engine. Right? If at all there is a self-ignition or auto-ignition. Self-ignition is a kind of ignition that happens only in CI engine. In CI engine, the combustion event will get started only with self-ignition because you are not using spark plug as we do in the SI engine. Ignition is not with the external aid, rather it's a self. That process is a normal process in CI engine, but it's an abnormal process in SI engine. We should not have the self-ignition. Once the self-ignition of the charge, fuel or mixture happen, then it leads to this knocking or abnormal combustion. So knocking combustion happens due to self-ignition of N gas. I have used the term N gas. N gas refers to the charge. Charge here refers to fuel plus air. Put together is charge. Okay, this is in gas phase. This is in gas phase. That's why we use the word N gas here. Self-ignition of N gas is what is going to create this knocking or abnormal combustion. Okay, so N gas is defined as a charge which is located at farthest distance from the spark plug. The charge that is located at a faraway distance from the spark plug is defined as an N gas here. Self-ignition of N gas is what is causing the knocking combustion or abnormal combustion. Okay, this is something very basic that you need to first get into. The self-ignition of N gas is what is causing the knocking phenomena, and the N gas is the charge that is located at the farthest distance from the spark plug. Okay, so we know that we generate a flame in the spark plug location. Once you generate the flame in the spark plug location, the flame in fact will form two zones inside the combustion chamber. One zone include burned gases. The other zone include unburned fuel air mixture. Okay, so what is behind the flame front is burned gases, which are nothing but products of combustion. What are the products of combustion? We analyze in chapter 2. When we do the thermodynamic analysis of combustion, we know what are the major products of combustion. So this is what will be there behind the flame front. What is ahead of the flame front is the unburned fuel air mixture. Okay, and this flame zone is a chemical reaction zone. Flame, in fact, is forming two zones inside the combustion chamber. Under the normal combustion, this flame generated in the spark plug location will move across, propagate across the combustion chamber, ignite the unburned mixture. The mixture at any point of time is ignited by the flame. Okay, then the flame moves and ignite all the mixture, entire mixture present in the combustion chamber, and thereby the combustion event will be a smoother normal combustion. Okay, at any point of time, the mixture is ignited by the flame. Under certain conditions, this knocking or abnormal combustion takes place wherein there is a self-ignition of the charge. And self-ignition is most likely to happen only with the N gas, not with any other charge. Let us see how. So I have provided here two profiles, pressure profile. This is a normal combustion based pressure profile. The second one is a knocking combustion or abnormal combustion based pressure profile. Just by looking at the pressure profile, you can say whether the combustion event is normal or abnormal. Pressure profile for an engine is like a cardiograph, like a ECG, which tells you how your heart functions, how well the engine functions can be inferred by looking at the profile, pressure profile. So you can say that the pressure profile is a ECG for the engine. Okay, so in a normal combustion, you see that the profile is smoother. You have a smoother pressure profile. Whereas in an abnormal or knocking combustion, you see the pressure profile is not smoother. There are pulsations, pressure pulsations, and this region is where the knocking is happening. So there are pressure pulsations, which is an indication of knocking or abnormal combustion happening in the engine. Apart from this is one inference. The second one, during knocking, the noise that is generated, combustion noise, we call it as combustion noise. Noise in an engine is generated not only due to combustion, there are also mechanical noises due to friction, wear in various components. Those are mechanical noise. Here we are talking about combustion noise generated due to very high pressure pulsations. Okay, that is audible to the human ear. You can hear it. Okay, you can hear the noise. Okay, that is another inference. So it's a physical inference. Okay, and by looking at the profile, pressure profile, you can also confirm that there is a knocking combustion. Now let us look at the mechanism, how this knocking is happening. So I have taken profile 1. Just look at. So here the point A is a spark plug location. This is where you have the spark plug. Okay. The flame is generated in the spark plug location, and there is another location called specified as D. In this location, what you have is N gas. N gas is a charge, fuel air charge, as defined earlier. This is a fuel air charge located at the farthest distance from spark plug. Here you have spark plug, point A. Point D is location of N gas, which is far away from the spark plug. So you create a stable flame here at point A. Then this flame is moving, as indicated here. Flame is moving across the combustion chamber, right? So flame moves at some velocity. We already discussed about this, and this velocity is normal flame velocity is based on physical process as well as chemical process. That's how the flame moves, ignite the mixture, okay, including the N-gas mixture. Now, what is happening during this flame propagation? When the flame moves from, say, location A to location D, there are several things that are happening, okay, in the flame region. So what is happening when the flame moves, right? So this is a reaction zone. Here you have burnt mixture. Here you have unburnt mixture. This burnt mixture will be at a very high temperature. Unburnt mixture will be relatively at a lower temperature. This is at higher temperature. So density of the burnt gas is considerably less compared to the density of the unburnt mixture. So this burnt products, because of their lower density, they will try to expand and try to occupy as much volume as possible. So there will be expansion of the burnt product because they are lighter, they are less dense. They expand and try to occupy more volume. In the process, it pushes the flame to move ahead. Okay, so it's a kind of burnt gases pushing the flame move ahead. Okay, and this flame movement will compress the unburnt mixture. And this compression can be treated as adiabatic compression. What do you mean by adiabatic compression?
Heat transfer is zero.
Heat transfer is zero. There is a heat transfer, but we are saying this as an adiabatic compression because the flame moves at a very high velocity. The time you give for heat transfer for this during this compression event is minimal or negligible. Because of this, it is treated as adiabatic compression. So the flame moves quickly since the burn gas expand and push the piston, push the flame to move ahead. This is like a piston compression. The flame is moving, compressing the unburned mixture. The compression of the unburned mixture, what will happen to the unburned mixture because of this compression effect? Pressure will increase.
The pressure will increase.
Temperature will also increase.
Temperature will.
So the flame is compressing unburned mixture, it's increasing the pressure and temperature of the unburned mixture. This is one effect. The second effect is the flame zone is highly reactive. The temperature here is very high. I'm talking only about the flame zone, not about the burnt zone or unburnt zone. I'm talking this thin flame. In this thin flame, the temperature will be very high. This will be typically well above 2000 K. So the flame will start to radiate energy, thermal energy. So from the flame region, there will be heat transfer, but convection and conduction is less dominant because of very less time available for heat transfer. Just now I mentioned about it. So there will be radiation mode of heat transfer that will be dominant since the flame is at a very high temperature compared to the unburned mixture. There is a delta T. So radiating mode transfer, heat transfer is going to take place. What will be the effect of this radiative mode heat transfer? The unburned mixture temperature is going to rise. Okay, so the temperature and pressure of the unburned mixture is going to get increased because of the heat transfer effect from the flame zone radiating heat. It's also due to the compression effect of the flame. Did you get what I'm saying? There is a compression effect. There is a radiative mode heat transfer effect. So the unburned mixture pressure and temperature start to build up. And this process continued to happen during the entire flame propagation event. During the entire flame propagation event from this spark plug location to the other location, N-gas location, there is going to be a progressive increase in the pressure and temperature of the unburned mixture, right? There will be progressive increase in pressure and temperature of the unburned mixture. Okay, meaning now you can imagine what will happen to the charge located at D. This is going to be subjected to this progressive increase in pressure and temperature for a longer time because the flame takes some time to reach this D, point D from A. So there is a progressive increase in pressure and temperature of the unburned mixture. Okay, and also what will happen, unburned mixture, since pressure and temperature is increasing, there is something called pre-flame oxidation reaction, meaning there is no flame formation, but there will be some slow oxidation reactions. Chemical kinetics will start to take place. Okay, and all these oxidation reactions are exothermic reactions, meaning they also release some heat. So the unburned mixture is subjected to increase in pressure, increase in temperature due to flame movement. It also undergoes this pre-flame oxidation reaction, which is exothermic, thereby its temperature is rising, right? So this phenomena happens gradually and there will be a progressive increase in the pressure and temperature of the unburned mixture which is located nearer to the flame as well as far away from the flame. Right. So now with all this mechanism, if the unbound mixture pressure and temperature is not rise to the self-ignition temperature, you know, with a given proportion of fuel and air, there is a self-ignition. We call it as a ignitable range. So if the unbound mixture is not rise to its self-ignition temperature or to its ignitable range, the mixture is not going to self-ignite. The flame will come and consume that mixture. Especially the N-gas mixture, which is located at the far away distance, the flame takes some more time to reach the N-gas compared to the other region. Okay, and this mixture is subjected to progressive increase in pressure and temperature, as we have just discussed just now. So in a normal combustion event, the flame generated at A propagate across the combustion chamber, reach B, where you have N-gas location. The N-gas is also consumed by the flame. Okay, because as N-gas is not rise to its self-ignition temperature or ignitable range with all the effects, whatever we have discussed so far. Now, you look at case 2. So again, A is spark plug location, B is the location for N-gas. In this case, when the flame moves, propagate across the combustion chamber, once it reaches this B dash, the charge ahead of it, indicated as C dash, has reached its self-ignition temperature. Once it reaches self-ignition temperature, the flame can move only from B dash to C dash. It cannot move beyond C dash, because what is happening, since this mixture is raised to the self-ignition temperature, another flame will start to the self-ignition of this mixture will lead to formation of another flame in an opposite direction. Another flame start to form in an opposite direction, and these two flame, there is a main flame front, there is another flame front moving in opposite direction because of self-ignition of this mixture. These two flames collide. These two collide and result in pressure pulsations as evident from the pressure profile. These two flames will collide and result in pressure pulsations as indicated in the pressure profile. Okay, so this self-ignition of the mixture is like almost instantaneous heat release, thermal energy release. There is a large thermal energy release in no time. And because of this large thermal energy release, locally you will have a very high pressure, almost 3 to 4 times higher than the average pressure. Suppose if the average pressure in the cylinder is 50 bar, the region where self-ignition is happening, local, that is the local pressure, it's around 150 to 200 bar pressure. 3 to 4 times higher pressure will be generated locally, momentarily, because of the self-ignition, because there is a large thermal energy release in no time. Okay, there is a large pressure generated locally, and this results in another flame forming and moving in opposite direction because the pressure difference is now different. Okay, so these two collide, this extreme pressure difference between this region and this region cause severe pressure wave. This pressure wave is what is propagating, and this pressure wave is what is striking the cylinder and cylinder wall. It will set it to vibrate. So cylinder wall will start to vibrate, and this vibration will also be felt in the crankshaft. Okay, so this vibration will be transmitted to the crank shaft region also, because the pressure waves are striking the cylinder wall, solid boundaries, and set it to vibrate. Okay, this is what is causing this high-pitched metallic ringing sound. We call it as a high-pitched metallic ringing sound. This is similar to striking this wall with a hammer. That's why it is called knocking. Knocking is like striking the cylinder wall with a hammer. Similar to that, pressure wave is doing the same process. Okay. So you can imagine the wall being hit by a hammer. Here the wave, pressure wave is doing the similar phenomena. The wave is striking the wall and set it to vibrate. And because of this phenomena, you hear, I said it's audible to human ear. The decibel levels are high. So you can hear the sound clearly at the time of knocking. Because the waves hit the wall, set it to vibrate. There is a noise, there is a vibration. Noise and vibration will happen locally around the N-gas region because there is another flame front form. There is a high thermal energy release and local pressure rise is very high compared to the average pressure. And this is what is causing this knocking, which is evident in the pressure profile. So there is an extreme pressure difference causing a pressure wave, and that wave strikes the wall, cylinder wall, set it to vibrate. Vibration will also be felt in the crankshaft. Okay, so the entire engine will start to vibrate because of this, right? So it affects the NVH characteristic. Mild knock doesn't damage the engine. Mild knock will happen sometime. Okay, it doesn't damage the engine, but there will be vibration that will be felt. It's a kind of discomfort. This is mild, but when the knock continues for a longer period of time, when it sustains, it may damage the entire engine. Okay, that's why it is an undesirable phenomena, right? So the most important factor here is the N gas should not be raised to the self-ignition temperature. That's why octane number, whatever we discuss in chapter 1, plays a big role here. When the fuel have sufficient antenna quality, it is not going to self-ignite because the fuel is resisting the self-ignition even. Once the fuel has a high octane number, it doesn't undergo the self-ignition process. That's why fuel quality plays an important role in avoiding knocking. So it takes some time for the flame to reach N gas. By the time the N gas should not reach its self-ignition temperature, meaning it should have a high octane number, right? And by the time the flame reaches, it doesn't undergo self-ignition. If that is the case, then it is a normal combustion. The flame is going to consume the N gas mixture. The combustion event is smoother. Okay, so the most important consideration here is the N gas should have sufficient antenna quality so as to avoid knocking. There are several other factors. We are going to discuss that in the next class. It's time up. I stop here. If you have any questions, I can take your questions. Okay, there are no questions. I will see you tomorrow 6 o'clock. Thank you.
Thank you, sir.
Thank you, sir.
Thanks a lot, sir.
Hello, sir.